Okay, so now we move on from the general case of hydrostatic pressure distribution over a curved surface into a special case, which is the hydrostatic pressure distribution over a flat surface. So one example is, consider this this dam with a flat surface, and consider actually this dam is submerged under a liquid of height H, capital H, we are, as you go deeper and deeper in the liquid, in the water, the pressure is going to increase, and eventually you're going to need to know what the net hydrostatic pressure force F due to this static pressure, hydrostatic pressure distribution is going to be. And instead of looking at the full dam, we are particularly interested in a flat surface, but with a more general shape, which is marked in pink here. And that area has a center of area. And what we're going to do, just like we have done before, we're going to pick an elemental area dA, and on that elemental area we're going to find the pressure, which is ρgh, and continue to we'll move on to find the net force on this area marked by the pink contour, and its point of action, which we will call the center of pressure, which we have seen before, and we have learned how to compute it. As well as we want to find the two components, the orthogonal components that make up the pressure force in other words, we want to find the direction of this pressure force, which because it comes from the pressure, it's going to be perpendicular. Okay, very good. So here is a side view. So now we looked at the overall picture, at the isometric view. Now let's come from this side, from the side of the dam, and look in this direction. And what you will see is the edge of the surface of the dam. And if you look from a top view, just like the view we were looking at before, you're going to see the contour. So these are two different views. One is the top view, which is the pink contour, and here is a side view, which is the edge view, where you see just a flat plate, a flat line, a flat line. Okay, so I think these are two different views. And now the center of this area, which we're marking CG, we're going to use it to reference our coordinate system. So it'll be the center of gravity of this area is going to be our origin for X and Y. And Y is pointing along the plate in the direction pointing to the surface. The plate is inclined at an angle theta. And then what we will do is we're going to take an elemental area dA, which is dx dy. So now if you look at it in the side view, that elemental area is submerged under a liquid of height h of x and y. And then we're just going to integrate that over the whole surface. The center of gravity, which is a geometric property of this pink contour, is located, its projection is located here, and it's submerged under a liquid of height hcg. And the action point, as we will find out, of the net hydrostatic pressure force over this surface is going to act on the center of pressure, and it's going to be perpendicular. So that's the net force. And we will see that the center of pressure is going to be at a higher depth than the center of gravity. So this is hcg, and this would be the height of the center of pressure, the depth of submersion of the center of pressure. So the center of pressure is always going to be deeper, as we will see. So here are the three things we plan to do. once we've taken this elemental area dA, and computed the elemental force dF, which is the dA times the pressure being the hydrostatic pressure, which is the rho gh at x and y, and then we're integrating over the whole surface. So let's do that. But before we go there, let's define a couple more coordinate systems. So our primary coordinate system is xy. So y is measures the distance from the center of gravity along the plate, and it points upwards. So that's our y. It's positioned at the center of gravity. And then we have another coordinate system, zeta, which has its origin at the surface of the water, and it's inclined at an angle theta, the same inclination angle as the plate, and it points in an opposite direction to y. So the center of gravity, so that's zeta. So that's zeta equals 0, and this point will be the distance from the surface to the center of gravity is going to be the distance zeta cg. So we can find a relationship between y and zeta. So y and zeta are point in opposite they're parallel, but they point in opposite direction. So that's why you have a minus sign, and they shifted by an amount of zeta cg. So if I were to take the zeta origin and move it to the center of gravity, I will just lose this zeta cg because y points upwards and zeta points downward, and they're both at the center of gravity. But that's not the case. The case is that the zeta coordinate system is shifted by a distance zeta cg from the center of gravity. And then the relationship between the submersion depth h and between the distance y or the distance zeta is related through the sign, as we see over here. So these are our so you'll see why we're using those coordinate systems. It's easier to work that way. So we have zeta, we have y, and we have the h, and then we have the sine theta is the inclination. The x is now into the page. If we're looking at the side view, it's into the page, and it points along the surface perpendicular to y. Okay, so now we've taken this elemental area, and we have the pressure rho gh. So let's do that. But before I move further, I want to remind you with something that you have taken in CIVE 210 in your statics course or in any geometric calculus course. If you have an area as the one marked by the pink contour over here, and I want to know where the center of gravity. The way you do it is one. So now you let's say. Sorry, let's just change to a pen. So if I want to know where this CG is, I've started with the point with the premise that I know where the center of gravity is, and I've located my coordinate system. But let's say I'm working. I don't know where my center of gravity is, and the way that I would do it, this is my, let's say, x and y. It's a different coordinate system. The way that I would get my xcg, so it's the distance between the center of gravity and the y-axis, that would be my xcg on this different coordinate system, is I will take an elemental area dA, right, and multiply it by x. So you'll get x multiplied by this elemental area that we have marked here. So that's my x dA. And you integrate over the whole surface area, and you divide by the surface area. So that would give you the location x of the center of gravity. So so that's by definition. And if I put something else other than x, if I'm looking at the ycg, then I'll just do the integral yda divided by the area of the surface. Or if I'm looking at the zeta, then it'll be the zeta dA. So remember this formula, the integral. So the center of gravity location relative to coordinate system F will be F dA divided by the total area. Okay, so this will come handy in a second. Okay, so we've taken our elemental area. We have the pressure ρgh. So my F is just the summation of that elemental force PdA, with the pressure being the ρgh. Now in this derivation, we want to do something different to what we did with the curved surface, and here I'm going to say at the beginning that I'm working with absolute pressures. There we said I'm working with gauge pressures. So that way you see what will happen in the end. So I'm just using the absolute pressure convention just because I choose to do so. So my pressure is not just ρgh, it's ρgh plus P atmospheric multiplied by the dA, and we said the dA was the dx times dy. So substitute. Now we have a relationship between h and y and zeta. If you go back 2 slides, so the relationship between y and zeta, and then h and zeta. So h is just zeta sine theta. So it's the distance, the depth of this elemental area is equal to the coordinate zeta from the free surface multiplied by sine theta. So that's zeta, right? Multiplied by sine theta gives me this vertical distance. If I multiply it by cosine theta, I get this horizontal distance, but I don't care about it. I'm just interested in this part over here. Okay, so let's substitute for h with zeta sine theta. So that's what we did. And now you want to look at this thing. So ρg is constant and the P atmosphere is constant. So the P atmosphere is a constant times dA. So you get directly the P atmosphere times A. We said in the previous lecture that it's only a single term that we have to add, which is the if we decide to go from gauge to absolute, which is what you see over here. So if I were to work with gauge pressure, the force will be just what's left. But if I started with gauge and now I want to work with absolute, I'll just add this P atmosphere times A. Right, there you go. But now you have zeta times dA. And the theta is a constant, ρg is a constant. So I want to focus on those two. And that zeta dA is this part, the top part of the zeta cg. So if I multiply by the integral of the area and divide by the integral of the area, that means I just multiplied by 1, which I am legally allowed to do. But then that term that's highlighted, zeta dA divided by the integral of dA, is just your zeta cg. So that's what you have here. So you get your P atmosphere times A. So your force, net force, is the P atmosphere times the area enclosed in the pink region. And you have ρg sine theta is a constant. And then you have this area that we multiplied with, which is over here. And the zeta cg is just the highlighted term. So that's what you get. And then zeta sine theta. Zeta sine theta is just the h. So zeta cg sine theta is just the hcg. So the magnitude of the force is just the hydrostatic pressure force at the center of gravity multiplied by the area. So the hydrostatic pressure force here in absolute terms is that multiplied by the area. Previously we looked at it as the average pressure multiplied by the area, which is perfectly fine, which is what this says here. The height of the liquid above the center of gravity represents the average location for the average depth, the area weighted average depth of this surface. So that is our net force, which was easy to get. And now we want to get its point of action. And to get its point of action, what we will do is we have computed a dF here, right, on this area dA. And now what I want to do is actually compute, for this force, I want to compute its moment about the center of gravity. So I'll pick the center of gravity, and I will get dF times this distance, the distance from this object, right, to the center of gravity, just because I've located my center of gravity at 0, is equal to y. So the moment dm is y dF. The moment of this hydrostatic pressure force around the center of gravity is just y times dF. And then I will find the moment of the hydrostatic pressure force over the whole area. So I'm integrating dm over the whole surface area, which is enclosed in the pink region. So I get the moment about the center of gravity due to the hydrostatic pressure force. And then I will divide by this net force, and that will give me the perpendicular distance between my center of pressure and my center of gravity. So the action point. Okay, so let's do that. So that's what we are doing over here. So we're getting the moment of the force around the center of pressure. So that will be the perpendicular distance. The moment around the center of gravity will be equal to the net force multiplied by the perpendicular distance between the action point of F, which is CP, and CG. So this YCP is the distance between CP and between CG. So let's find, so that's a side line. So now we're really computing this M about the center of gravity. So the moment around the center of gravity, as we have said before, is the y dF, with the dF being PdA. So here's what we get: y times p times dA, that's a moment. And then we'll just proceed as we have done with the net force. For the p, we'll have the atmospheric pressure plus the rho gh, and the h is just the zeta sine theta. And let's now go to the y system, coordinate system, because I have y here, I have zeta here. Let's just replace one or the other. So let's just set for zeta, zeta c g minus y. So that's what we will do over here. So I get this first term is y times p atmosphere times dA, and then I have so as we said, this zeta, I'm going to replace it with zeta cg minus y. So now this zeta cg is going to go here, times a y pda, which is here, and then I get minus y, so minus y dA times the rho gh. So let's look at each one of those terms. The integral y dA, so we'll do the same thing. We'll divide by the area A and multiply by the area A. This looks, the p atmosphere is constant, so it comes out. So the y dA divided by A, so this whole thing, the integral here, is just A. right? So what does this look like? Y dA divided by A, X dA divided by A. So that would be YCG. And by definition, the Y location of the center of gravity, by choice actually, we chose to place our origin at the center of gravity. So my YCG is identically equal 0. So this is 0 by choice of placement of the origin of the coordinate system. And same thing here. I get YdA. So zeta CG is a constant. It's the location of the center of gravity. Everything here is a constant. So that's also YdA, which is also 0. That gives me 0, which is here. And then I'm left with y squared dA, which would be my moment of area. So if y dA is the first moment of area, this is which is the centroid, that's the second moment of area, which is the sort of moment of inertia or moment of area, if you will. So that we will call the IXX from your CIV, from your statics course or from your geometric calculus. So we found the moment about the center of gravity to be equal to rho g sine theta times the IXX. So there's actually a minus sign. Then we will equate it to the F times the perpendicular distance. We called it last time L perpendicular, so keep it L perpendicular so that you don't get confused. YCP, we just came up with that. So M is F times L perpendicular, and the L perpendicular is the distance between the center of gravity and the point of action of this F. The point of action of this F is YCP, so now it makes better sense. So we'll take this the F times YCP, and equate it to the moment that we have found, the moment of the distributed hydrostatic pressure force around the center of gravity. We will equate them. So now I can find my YCP. So I'll just take the F to the other side, so I'm dividing by it. So my location of the center of pressure relative to the center of gravity is rho g sine theta IXX over F, and it has a minus sign. IXX, because it's a y squared dA, is always positive. The sine theta is positive, rho g is positive, the F is positive. So YCP is a negative number, which means it's in the opposite y direction. So which means it's always as we started by predicting, it's always going to be located at a higher depth. The action point of the net hydrostatic pressure force F is going to be, this is the action point, which we call CP, is going to be located at a higher depth than the center of gravity, which is located at a depth of HCG. Right, and then we can do the same procedure again and find the in the plane, along the plane. So now we found the Y, and then we can pinpoint the location along the X where the where the XCP along this plane, where the XCP is going to be. We found the YCP, but now we want to find the XCP. So we'll do the same story. We'll end up with the IXY rather the IXX. Now the IXY is just, the definition of it is the integral, just like if you look at the y squared dA, it's going to be x times y times dA. That's the definition of it. And unlike the y square is always positive, the x can be positive or negative, the y can be positive or negative. So this thing can be positive or negative, which means it could be to the left or to the right of the center of gravity. So either solution is, or either possibility is valid. So now the reason why we did this is that these are common formulas that you can just use right away, and we summarize them here. You get the magnitude of the force, the location, the depth, if you well, it's not necessarily the depth, the y location of the center of pressure and the x location of the center of pressure. And the minus sign tells you it's in the negative x or in the negative y direction. But this IXY can be positive or negative. This could be to the left or to the right. But since everything here is positive, the YCP is always at a higher depth than the center of gravity. So we found the force magnitude, the net force magnitude due to the distributed pressure force, and we found its action point. And now if I ask you to tell me what this hydrostatic pressure distribution that we started with, what does it look like? Well, what is the pressure at this point? It's rho g times h, so plus p atmosphere, of course. So that's rho g times h plus p atmosphere. And this is a higher depth, so it's rho g times a higher h times higher rho gh. So this is the pressure distribution we're talking about, and it's linear, right? So excuse my graphing abilities with the mouse. So it's a line, it's a straight line. Unlike the atmosphere, where we had a power law distribution of the pressure with depth, because we had a variable density. Here we have a constant density, so we have a linear variation of the pressure with depth, or with distance, because depth and distance y along the plate are related through a sign, which is a constant. So now we have come up with, or we discovered that we need geometric features of the area that we're dealing with. We need to know its center of gravity. So that's for any surface, you can compute it. We need its area moment of inertia about the y-axis, so it's the IXX. So if we look, sorry, the tendency to rotate around the x-axis. So let's look at what the IXX is. If I take an axis going through the x-axis and I try to let me take the x-axis here, and I get two areas. Area 1 in fact I get the same area, but the distribution of the area is different. So that same area, I will just, so I have A and A prime are equal. That's A prime. And I want you to tell me which one has a higher moment of inertia around the x-axis. Which one is easier or harder to rotate around the x-axis? So you'll notice that this area has more, or this distribution of area has more of its surface area distributed farther away from the x-axis, from the x-axis. So you'll get the y squared dA to be higher. But here the x squared times dA, the x squared part of it, the y squared is actually much less. So area A prime would have a higher moment of inertia than A. It would have more resistance to rotation around the x-axis than the area A. A prime is more resistant to rotating around the axis X than area A. Now let's look at what it means to have an IXY. So let me draw this. Let me give you two examples. So I am running out of space, so here, let me just okay, so let's take two cases. Case 1, and as you can see, this is x, this is y, and case B. So I have two different areas. So now imagine you have this area and you have two axes going through it, and now you try to rotate this area around the x-axis. If you try to rotate it around the x-axis, it will rotate around the x-axis. If you rotate it around the y-axis, so if you put your hand in here and just spin it, it'll just spin around the y-axis. And so the two motions are completely independent, completely decoupled. So a tendency to rotate in the x-axis is independent of the tendency to rotate in the y-axis. However, if now I put my so I have my x-axis, my y-axis, and I have this triangular area. If I put my finger here and I try to push into the page, because I'm trying to rotate this thing around the x-axis, I will also get a tendency, so I will rotate around the x-axis, but at the same time my object will also rotate around the y-axis. So these two motions are now coupled. They are not completely, because of the lack of symmetry that we have here, the two motions will be coupled. So the IXY is the tendency to rotate around the y-axis if I try to push it to rotate around the x-axis. So it's the coupling of those two motions together. And you will see those three properties: the center of gravity, the moment of inertia, and the coupled moment of inertia for different shapes. So here you have a symmetric object around the center of gravity. So the first thing is you place your center of gravity. It's a rectangle. The area, we know it. The IXX is the BL cubed over 12. So one thing you need to pay attention to here is the y-axis. So when you're solving problems, y was our main coordinate, which indicated sort of the direction towards the free surface. So you want to keep, because there's B and there is L. B is along the X, and Y and L is along the Y. So you cube the L, not the B. So it's BL cubed. That's going to make a big difference in your calculation if you make a mistake. If you mistake the B with the, because you have a rectangle when you have a problem, and then you'll just say, when you're doing the calculation really fast, sometimes you can interchange the B with the L, because you say, oh, it's a rectangle, and if they're different sizes, then you can get a huge amount of error in the IXX and in your solution. But what you'll notice here, because of symmetry, my two motions are completely decoupled, IXY. Same thing with the circle. Its area, its IXX, and its IXY is 0 because it's completely symmetric. Now look at a half circle. You look at the area. That's your area, that's your IXX, and now your IXY, if you try, so here, because of the symmetry, if you try to rotate your the symmetry around the y-axis, if you try to rotate around the x, there's no tendency to rotate around the x-axis. But now look here at this triangle. If you have its area, have the height times the base, and you get the IXX. But look at this distance to S. So here's your S. So when you're completely symmetric, the B minus 2S will be 0. So you have complete decoupling of the two motions. But when you have lack of symmetry, when that is non-zero, you're going to get a tendency to rotate in one direction when you rotate in the other direction. So that is the force around, that is the hydrostatic pressure force on a flat surface. And here we're looking at different planforms. These pink lines that we're looking at is this pink contour that we have over here. So this pink contour, we've shown it to be that it could be a rectangle, a circle, or it could be any shape that you could ever think of. And it comes from the parameters of the problem. And now here's an example of multi-layered fluid. Same story, you solve each problem on its own, and you sum the forces. So each layer of fluid of depth, certain depth, Z minus Z1 and Z1 minus Z2, fluid 1 and fluid 2. Each one would have its own force, its own distribution, and it would have its own CP and its own, so you'll see it will have its own center of gravity and its own action point, CP. So you'll treat each problem alone. This is area A1 or A2 with CP2 and CG2, and this is area A1 with, that's area A1 with CG1 and CP1 and so on. And then the net force is just the summation of the two of them, and you just weigh it. So you weigh the distance, you get the moment from the two forces divided by a distance, a known distance, so that so you get the moment around any arbitrary point, and then you'll get the distance from the arbitrary point to your net force. Okay, so now before we solve a problem, I would like to do this. So now we have talked about the hydrostatic pressure distribution over a curved surface. Then we took the special case of a flat surface. So these were areas and surfaces. And for the flat surface, it was we got some quick formulas that we could use very quickly if we had our geometry nailed down. So we didn't have to do the integration from scratch. But now, what if we have a volume